Hello again. This is the second lecture on flat slabs. So now we'll be discussing the drop panels and column heads. The drop panels and column heads they create several advantages. First, there could be an architectural point of having a column head if you want. Also, the point is that you are having an increased thickness at the location that you need most, which is around the column. So this will do several things. First, that it will increase the thickness at the location at which you need to protect the column and the slab at the column for punching. So now you are less susceptible to punching. Second, you are increasing the depth at the location of the maximum moment that we are talking about here, which is the negative moment at the column strip. So, in order to consider the drop panel effective as a drop panel, the additional thickness, the TD or the drop thickness, should be at least 1/4 of the slab thickness. The drop width should be more than the parallel dimension over 3 and less than the shorter dimension over 2. This is why in most of the cases they take it as simply the shorter dimension over 2. The column width, as mentioned previously, should satisfy that the clear height it should be the bigger of the clear height over 15, 300 millimeter, and the parallel dimension over 200. The column head width, if you are using a column head, should not exceed the shorter dimension, which is actually the shorter span, which is making sense. I mean, you could not eat the more than the span. You could not take a dimension that's more than the span. So practically speaking, actually, this is the maximum dimension of the column head width. So the punching shear, again, if we go back to the concept, the punching shear, we said that it occurs at the perimeter of a distance of t over 2 from the face of the column. But here we will have another issue, that where is this d over 2 measured from? So previously, if we don't have a drop panel or a column head like what's shown here in figure A, you are taking this d over 2 simply from the face of the column. Okay. However, if we are talking here about a case of having a column head without a drop panel, the d over 2 is measured from the end of the column head. Okay, so this is the location of the plane of failure. However, the third case, which is shown in shape C, is simply you are having a drop panel without a column head. So now you could have several planes of failure. One of them is d over 2 from the face of the column. The other is d over 2 from the end of the drop panel. But actually, this would be very of a very large area if you take the d over 2 from the face of the drop panel. So typically, the more critical would be d over 2 from the face of the column. However, again, it is less critical than if you don't have a drop panel from the first place, because this location is of a higher thickness. Additionally, if you have both together, a drop panel and a column head, then you are talking about a case where you have again the same two planes of failure, d over 2 from the face of the drop panel and d over 2 from the face of the column head. In such case, the loads will change a little bit, because now you have a drop panel, so you need to adjust for the concept of having the drop panel itself. So now you are talking about a case where you have an additional weight of the drop panel that will need to be redistributed all over the whole cross section. So simply you will calculate this additional weight, which is gamma c times td times s short times s long, and divided by the L long times L short. So now you will add this weight of the drop to the flooring and the wall weights and the whole big chunk of weights, and multiply it by 1.4 and add it to 1.6 W live load, this will give us the total ultimate load. The total static moment M node, again very similar to what we did before, is W ultimate L short times L long minus 2D over 3 all squared over 8 for the long direction, and then you swap the long and short, L long and L short for the short direction. And again, if you, as mentioned previously, D is either the width of the column if you don't have a drop, if you don't have a column head, or the width of the column head if you have a column head. So this is another advantage for having a column head, which is the concept that you are actually decreasing the moment itself. And this total moment is distributed on different locations. So, but there is a little bit fine tuning here. You need to understand that there is an additional reinforcement for the column head, okay, to distribute the stresses properly within the column head, as you could see here. And there is an additional reinforcement in case of having any openings within the flat slab. So let's repeat the previous example that we have done in the previous video while using drop panels. So first, the dimensions as previously done, 6 over 5 is 1.2, so the simple method is applicable because this ratio is less than 1.3. The slab thickness now will be a little bit less because now it's, instead of the 6000 over 32, it's a 6000 over 36. So now we could go as low as 180 millimeters. The column width should be the largest of 300 millimeters and 3300 over 15 and 6000 over 20. So the 500 millimeter is okay. Again, the same thing is for the edge beam, but now you don't need as thick as an edge beam as the one we did previously, because it's 3TS, so it's 540 millimeters. So you could simply take it as 550 millimeter instead of the 750 we have taken before. So now you could notice that everything is getting lighter now. The slab is lighter, the edge beam is lighter, so you are actually saving in concrete by having a drop panel. The drop panel is assumed as squared, and the side should be more than 6000 over 3, which is 2000 millimeter, and less than or equal to 5000 over 2, which is 2500 millimeters. So simply take the drop panel to be 2.5 meters by 2.5 meters. The TD, the drop, should exceed quarter of 180, so which is 45 millimeters. So take it as 50 millimeters. So the total drop panel thickness will be 230 millimeters. The column strip will be, if you have a drop panel, the column strip should always be equal to the drop panel width. The field strip short direction is 5 minus 2.5. This is 2.5 meters. The field strip long direction is 6 minus 2.5. This is 3.5 meters. Then the load calculation, the drop panel additional weight is simply 25 times the additional drop dimension, which is 0.05, times the 2.5 times 2.5. Then you will divide this weight by the area, which is 5 by 6, and add it to 1.5 plus 2 plus 0.18 times 25, which is the own weight of the slab. All of that will be multiplied by the 1.4, because this is our dead load, plus 1.6 times 4, which is the live load. You will notice here this value is 17.97 approximately kilonewton per meter square. If you compare it to the value in the previous example, example 1 in the previous video, it was 18.3. So we have got this structure lighter a little bit. Then you will check for the punching. So only interior columns will be checked because we already have an edge beam. So B1 is equal to A1. Now, instead of having it added, if you remember, it was 500 plus 175 before. Now it is 500 plus 205 because the thickness has increased at this location. So 205 is actually 230 minus 25. So this is 205. So the perimeter actually increased more. 4 times 705 is 2820. The same beta 1.15 for interior columns. Q up is more or less near to it, is 530 kilonewtons. The stress now will significantly get less. So if you compare this stress, this punching stress, to the punching stress in the previous video, in the previous example, you will find this one is 1.05 megapascal because the area has increased. The punching area has increased. So now this thing will have less stress. Again, the QCU up is the same 1.3 megapascal. It didn't change because the properties of the concrete is the same. However, it is significantly now larger than the punching stress. So now I am more safe. In the previous example, both of them was 1.3. So both of them were 1.3. So it was a little bit critical. But now we are more safe. We are in a more safe condition. So we have a good room if any load increases or whatever thing happens. So then you design for long direction strips. The column strip is 2.5 meter wide. The field strip is 2.5 meters wide. Then you will calculate M node. D, of course, will change depending on location, because if you are talking about a field strip, it's is different than the column strip, specifically beside the column, because the location at the column, it will have a larger D. So you could see here that D at the column is 205 millimeter, while everywhere else is 155 millimeters, because there is a 50 millimeters difference. So this will change the AS minimum. Here it's larger. It will change the R1 omega calculation. So now I need less area steel than compared before. Now I'm talking about here 6 phi 10 and 5 phi 12. If you recall the previous example, it was 5 pi 16 instead of 5 pi 12. So now I reduced the amount of steel that I need specifically at this location. The others are the same. The 6 phi 10 and 10 phi 10, they are the same. But this one that carried the heavy big chunk of steel, this amount of steel has been reduced. Very similar issue is in the short direction. But remember, the field strip is 3.5 meters wide, not 2.5. The M node short, very similar calculation. You will multiply the W ultimate by 6 by 5 minus 2 times 0.5 over 3 all squared over 8. And again, the D is varying. But bear in mind here, because here you have this is the secondary dimension, so you need to deduct a further 10 millimeter from what? From your D. So this D is 195 millimeters, not 205 millimeters. Okay, and the others are 145s. But again, you are having a less reinforcement, a less amount of reinforcement than when compared. Even here, it became 5 phi 10 instead of 6 phi 10.